Exercise 16D, instantaneous rate of change. So as long as we remember what a rate of change means, this one is not as challenging as it might initially look. The only thing that is challenging for students I find with this particular exercise is that your answers will not match the textbook, and that is because it's all about approximate values. If it were me, the only thing I'd worry about if I'm checking my answers with the book is if I'm vastly out by several, like 10, 20 or 30. And as long as I'm in the right direction, as long as it's positive or negative, it's fine. So what's instantaneous rate of change is all about? So far we've talked about a constant rate of change, which is the same rate of change for each part of the graph. We've looked at the average rate of change. So we've taken a point and a point here, and then we found what the distance or the average rate of change between those if I draw a line. Well, an instantaneous rate of change is trying to approximate. So it's trying to approximate. If I wanted to find the instantaneous rate of the change right there, at that point in the line, what is it? Now, theoretically, this is impossible because you need 2 points in order to calculate a rate of change. We need a y2 and y1 and an x2 and an x1. We can't just find the rate of change of an x1 and a y1. So we need to find other ways to approximate this. And one of the ways that we can approximate this is using a thing called the tangent line. A tangent line is the idea of a straight line that touches a graph only once, and it just touches that graph and keeps going. And we can find that line and use that to calculate the gradient. Because if I find a line that just touches the 1 point that I'm looking for, that point and that line will share this same gradient. So a tangent line and that point will share the same gradient. That is a fact that it will be very, 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 very helpful for you to remember for the rest of calculus. As long as you remember a tangent line and the point at which the tangent line meet will have the same gradient. Now, let's have a look at this particular business. We've got this graph here, and we want to find first of all, we want to find the average rate of change between x equals 2 and x equals 3. So we can do that. X equals 2 is about here at this point, and 3 is at this point. So we've got 2 and 70. We've got 3 and 0. So the average rate of change will be 0 take away 70 over 3 take away 2. So it's negative 70 over 1. So that's negative 70. So that is our average rate of change at this point. Now what we're going to do is we're going to estimate the rate of change when x equals 2. So how do we estimate it? So we want to find the rate of change at that point. So we can do this a number of ways. One of the ways that we could do this is zoom in the line and try to find the nearest possible known points that we possibly can do. As in, so we take a couple of points. So because I've got this lovely and zoomed in, I might hover here and hover there. So what I've done is I've narrowed the graph. I'm just taking that small section of the graph there. That is going to be, let's go and zoom down. How far away are these? So that is about 2/3 of the way of this. Now, how many? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is broken up into tenths. So I'm going to suggest if this is about 2/3, almost a half, it's slightly more than a half, I reckon. So this would be 2.06, I reckon, and it's right on the line here. So that is going to be at 65. And then this is going to be, if that was 2, and that's going by 10, so that's going to be 1.9. I reckon this is going to be 1.9. Well, that's closer to 5. Let's say 1.94 over 60 something. Which one is that? That is going to be, that's 75. So we're approximating the instantaneous rate of change. The best way to approximate it is to make the distance between the lines as close as possible. How close though? You want to close it such that that looks like a straight line, like the 2 points make a constant rate of change. Because if they make a constant rate of change, then constant implies that it's the same gradient for the entire part. So that's what I'm aiming for here. So if I wanted to find the rate of change at exactly that point, I can do m is equal to, and we'll zoom out a bit here, 65 take away 75 over 2.06 take away 1.94. And I should left my negative sign. So negative, so it's 8. 1 over there, so it's negative 8, 3.33. So it's approximately negative 83. And now what we can do is we can use a tangent line. So I've already drawn the tangent line here. The tangent line here is I've drawn a line that hits the graph only once, and I've got 2 points here. So I've drawn a line. This is, I find, really hard, especially trying to do it in the textbook questions, because you're just trying to find a point that hits that graph once. And we'll find the average rate here. So the average rate of this line should be a model to find the instantaneous rate of change at that point, because remember, the tangent line and that point will share the same gradient. So this will be m is equal to y2 minus y1 over x2 minus x1. And this is going to be 0 take away 105 over 2.8 take away 1.6. So negative 105 over 1.6. So that's going to be, come on, 1.2. One remainder, so that's going to be 7 and 87.5. There we go. So, and it should be a negative, because it's I keep forgetting my negative sign. So, and that's a common mistake, is people forget their negative signs. So there we go. So you can see that I'm actually not too far off with my little approximate here. I've got negative 83. This is negative 87. So you can see that the genuine instantaneous rate of change must be somewhere in between those two. In the next chapter, chapter 17, we actually look at a way that we can actually find the real, or as close to real as we humanly can, the real instantaneous rate of change. But hopefully you've now got enough there to help you out with chapter 16, looking and introducing yourself to rates of change.